Okay, so let's start our today. So actually I was not sure whether this relation holds. So let's just leave it here. So uh, 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 log of AB is equal to exactly log of A plus log of B, or up to mod 2 pi I. Okay. Yeah, so maybe let's say up to like a 2 pi I z. Okay. Okay, so maybe let me try one more. So so okay, so let's try. Let's give one try. So this is by definition the real log of modulus AB, and then plus I times A of the product AB, right? And then so this is equal to the real log of modulus A, and then plus the real log of modulus B. So let's erase the 2 pi I for a while. Okay, so let's just work on the equation that happens to be the two sides of this equation. And then so plus so the imaginary parts, this is the I of the argument at A, and plus I times argument at B. Okay, so so we know for sure that for the real log, right? Real log of AB is just equal to the real log of A times plus real log of B, right? So e to the, yes, okay, I think e to the, shoot, let me check. Okay, yeah, so we do have this. Okay. Okay. Yeah, I think maybe previously I made a mistake. I think when I say using L'Hopital's rule with the log of some equation over log. Oh, this is a different thing. This is like a log of something over log of something, right? So this is a different thing. Okay, never mind. So I just talked about something that I did before that I erased already. Okay, so the question is that the question becomes so is the I times the argument. So namely, is the argument of AB equal to the argument function that we have of A plus the argument that we have at B? I think yes, because I think it really depends, right? Because suppose that suppose we have the argument function. Let's say, yeah. Let me just erase this part. So, I don't think this is true in general because, for example, if we take the principal log, so for example, let's see, so principal log maybe is not a very good example. So take the, so that, let's use LZ, okay. So let's use a different letter. That's, so what I want to say is that, so here this is a hole, right? So I want to puncture out this disk. So let's say it goes from C minus the point 0 yeah, so I times 0 to infinity, right? So namely, all the positive imaginary axis is being deleted to C. Okay. Let's say so in this case we just let Z yeah, so be the branch of log such that L of 1. So the angle at 1 is exactly equal to 0. Okay. So in this case, so yeah, so it is well defined. It is well defined because for each point, we have already fixed a continuous choice of the argument function, right? Okay. So then what happens is that, so, and then this is given by, so then we have 2 points, right? So basically, we pick, so I'll just pick 2 points. That's these 2 points. They both lies in the first quadrant, right? And then, but their product may lies in this one, so that these 2 points after multiplied together cross the division line. Okay. And then maybe, so let's see. So pick A to be pick Z1 to be, let's say, just e to the I, let's say power 6 or power 3. Okay, let's say e to the I power 3, and then Z2 is equal to e to the I pi over 3 again. Okay, so hold on. So what am I gonna say? Okay, so what I want to say is that, so, okay, so we know that, so after we take the, so L of Z1, right, which is equal to L of course, Z2, which is the same thing. Okay, so, okay, let me use letter Z2 for even though, okay, so which is equal to, so in this case, the real log of 0, which is equal to, the real log, so this is the modulus 1, right? So the real log of 1, which is equal to 0, plus I times pi over 3, right? So that, yeah, so therefore, we have these should be added together. Okay, so L of D1 plus L of D2, which is equal to just I times 2 times power 3, right? Okay, so however, we have L of, so in this case, Z1 times Z2, so which is equal to e to the I 2 pi over 3, right? So basically, there are points over here. And then, so given the continuous trig of the argument function, so this corresponds to some negative angles, right? So that if we take the log of this one, so the argument function may not be 2 pi over 3 anymore, right? Because if it goes in this way, the angle will become negative for the log function. Okay, so that they will not match each other. Okay. Okay, so yeah, so I think it is in general not true for, at least I think it's not true for any log. Okay, at least it is not true for this log. Okay, so let's see, can we still work on this one even without assuming this property? I think maybe we have to encounter like some add or subtract of a 2 pi I, right? So let's see. So okay, so oops. Yeah, but we do have the property that after we take the we do have the property that we get the equality up to a sum of 2 pi I z, right? So we do have that, okay. But we just don't have the equality, okay. So okay. Or maybe there might be some trouble. I think we may need this property because if we just keep constantly tracking because literally speaking we want to break it up into let's say sum of the logs, right? So if as long as there's one break, we add a tuple I. So I don't think it would be friendly to our convergence argument. So I think we still have to somehow need the property, but based on what I did, I think there's a way to completely cancel out the tuple I argument. So I think what we need is that I think we need to pick the log function. You remember that for the log function, there's a separation line that we define for the log function. So I think we need to pick that line very carefully, such that when this omega I is very large. Wait. Yeah. So when this omega I is very large, the product, because when the omega I is very large, right? So remember, like this 1 minus z over omega I, they just so this is like a 1. So when this omega I is very large, this 1 minus z over omega I just lies. It's very close to 1. Okay, so this is very close to 1. So so basically what we need is that yeah, so we can pick the separation line because there's only finitely many points. Let's say is after we shrink the disk to be very small, right? So there is only finitely many point that's outside the disk, and then there's all the tails they lies inside the disk. Okay, so basically what we can do is that we can pick the separation line such that avoids the product inside inside this disk. So what I mean is that so that there won't be the behavior that I just described happen, right? So such that if I pick any 2 points, wait, shoot. Wait. I think there's still a problem because even though I do that, right? So because here I'm taking the product consecutively, right? Yeah. So what I'm saying is that so for 2 things, right? So if I take any of the 2 products, then if I take any of the 2 points, let's say A1 and A2 inside this disk, and then so okay, so basically the idea is that so method, right? So first, so we can pick, okay, so we can pick the ray let's say well, let's call it the division rate for the log, okay. Log function for the log branch function, okay. Such that so for any such that for for large n, okay, n, i.e. The point 1 minus z over omega I will stays inside the disk. Center 0 radius epsilon. Okay, so I assume that we pick epsilon first, and then for there is the n large, such that this one belongs to this epsilon disk for all I bigger than n. Okay. We have so how I gonna say this? So we have the product, right? 1 minus z over omega I times 1 minus z over omega j. So any of these 2 points will, so how I gonna say, will not cross the separation line. Okay, so because I think it depends on because the 2 point I pick, it can lies on the upper plane. It can also lies on the lower plane, right? So if they lies on the upper plane, then maybe I need to find a way to define these 2 points based on the angles. Okay, so maybe let's say that won't cross. Okay, so let's maybe we can make it strict like later. Okay, so won't cross the ray. So let's call this. Let's specify this ray. So let's call it. Basically, I just want to give a specific angle that account for the ray, right? So e to the I theta naught. Okay, e to the I theta naught times 0 to infinity. Okay. And okay, so I think I can make it more precise. So so first, I need to say that okay, so I think maybe I need to define the. Wait. Yeah. Okay. Okay. Yeah. So let me first I want to define like because basically when I multiply these two numbers, right? Basically because I only care about the angles. So basically when I multiply these two complex functions, complex numbers, basically I think the thing I care is that they're for the product these two angles are added together. Okay. So what I want to say is that uh uh mm, so what do I really mean? Okay, so I think instead of defining the I think instead of defining um if instead of defining this in a point wise uh definition, because I think because for the point, right, there is a probability that I was thinking of both two points lies in the upper plane, and there could also be the probability that one point lies on the upper plane, one point lies on the lower plane. Then their products will go all the way down below, right? So, and there are still the probability that the one up and one down, these 2 points will goes above. So it's in general very hard for me to. So basically, it's hard for me to define like using so if the 2 points is lies both lies above, right? So I can say that so yeah. So what I want to say is that so yeah, I want to define what do I mean by not crossing the line, right? So basically, I want to say that if the 2 points they both lies above the upper half plane, if both points they both lies sort of in the upper plane, right, in the upper disk, then the multiples the two angle after they sum together, it won't exceed like a certain angle. And then if the 2 points both lies below the real axis, and then after their these two angles being added together, then they won't exceed like these angles. But I figured out that the situation might be a little bit complicated if I allow if there could be the possibility where there's 1 point lies above, 1 point lies below. You need to really specify like which angle sort of dominates one another. If this one dominates, then the product is like will go up below, right? So then I should use like this like a bigger angle to evaluate. And then if it is in the other way, where the angle above sort of dominates the angle of the point above sort of dominates the angle of the points below, then I should use like this angle. So it's a little bit difficult to sort of define pointwise. So of like not crossing, of like what do I mean by the 2 points not crossing? Yeah, it's a little bit hard to define. So what I want to do is that because I can eventually pick the circle to be really, really small, right? So because when a circle is getting really, really small, the possible angle that the points can be is getting smaller and smaller, right? So what I can do is that I can shrink the disk. I can shrink the epsilon to be very small, such that for any 2 points, whatever I pick, they will not even touch, right? So I think I can do that. So yes. So let me just do that. So so such that for large n, yeah, but still I need to yeah, so I think I need to still need to specify what they mean. So yeah, so won't okay, so let me say this one. So okay, I think maybe I have to do that. So we first we define so that theta from theta from let's say from state to real. Actually, not state to real, but because I want the theta to sort of, because for the log function, right? So this is like because for the points lies on the upper plane, the angle should be positive, right? So basically, like pi over 3, like pi over 6, pi over 4, or pi over 3 or something. The angle is like positive, and then as long as it goes down to the negative plane, so the angle becomes negative, right? So basically, what I want to define the same idea. So basically, I think it's just the regular angle, right? So basically, from, let's say that it starts at 0 and then it goes to pi, right? So I want it to stop at pi, and then from here I want to stop it at negative pi. So negative pi to pi. Okay. Shoot, there is a trouble. Okay, so let's just first do that. Okay, so see if it works. So, and then what we do is that, okay, so be a continuous choice of argument function. Wait, it is continuous. Is it continuous? I don't think this one is continuous. Yeah, I don't think this is continuous. Hold on. Okay, so what is the time now? Okay, so maybe I think I have to stop here. So I'll just continue to define the okay, so maybe I think I'll just say it right now. Okay, so won't cross. Okay, I just say it, and maybe I can specify later. So won't cross the ray. Okay. And then yeah, so then what happened? So yeah, so such that yeah, I think yeah, so what do I want to do now? So so I want to use the log to sort of cancel out the. Yeah, I want to use the GU. I want to use. Yeah, after taking the log of this guy. Okay, so. Okay, so after taking a log of this guy, then after taking a log of this guy, it would cancel out with the first two terms of this function, right? So okay, so yeah, so I think maybe I'll probably continue next time by saying that if I take the log of 1 minus u times e to the u plus 1/2 u squared. Okay. And yeah, so I just I'll start with this one.